Hello, my name is Nathan Worsham, and this is my project, Ham, Spam, or Sham, for Regis University MSDS 696 Practicum 2. Since the inception of spam filtering, there has always been a distinction made between good emails, also known as ham, and junk or unwanted emails known as spam, but a third category of emails missing from this juxtaposition, which really is a subcategory of spam emails known as phishing emails, has become increasingly more important as it is a staple vector for malicious activity. A phishing email comes in many flavors, but essentially its purpose is to trick a user to reveal any sort of information, including a username and password, or to get the user to do an action on the attacker's behalf, like wire money, send sensitive data, or execute code. Often the message is meant to look legitimate, but may contain links to a fake website, which I dub a masquerading link, because the user thinks they are clicking on a good website, but in reality they are going to a bad one. For this practicum, I chose a real problem experienced at my place of employment. Currently, we provide employees a quick and easy way to report phishing emails at the click of a button. However, employees don't necessarily always use it correctly and confuse spam with sham emails. This requires a resource, a SOC analyst, to spend time deciding whether or not to investigate if the email is really a threat or not. So the question this project proposes to answer is to see if machine learning can be used to make the decision of whether an email should be further investigated or can be ignored. Furthermore, I would like to see if the final model can be run on Splunk, as it makes the data pipeline easy, and in my previous practicum, I built some text processing tools for Splunk that could help facilitate this. I had a collection of the emails in question, which were already classified into two categories by our SOC analyst. The majority of emails were sent as an attachment to another email. This retains the headers of the original email. In fact, I would have to throw out those that did not follow this procedure. Here I needed to extract the inner email and then extract the data in question to create features. Turns out emails are a bit complicated, and my understanding of them may not be complete. All emails include both headers with info like sender, recipient, and date, and a body. Often this is in MIME encoding, which supports all sorts of content and attachments. The attachments are known as payloads, and as mentioned before, a payload can be another message. To both extract and parse the emails, I mainly relied on the Python library mail parser. I then made features from the emails based on general statistics and information security domain knowledge. I then used this same library to create a Splunk app to package this extracting and parsing of an RFC 5302 compliant email inside of Splunk. For exploratory data analysis, I undersampled the ignore class to balance the target sets. One of the most interesting findings is that body length, meaning a simple character count, is a very good indicator of class. Here we can see that investigate emails are often much shorter, and the interquartile ranges between classes do not overlap. Thinking about this makes sense as these investigate emails are created by real people who likely elect to go an easier route and write brief emails, whereas a marketing email, which appears often in the ignore pile, is filled to the brim with HTML formatting, trying to stand out. Another feature of interest is the top-level domain of the sender. Ignore emails are more likely to come from a .com domain, while investigate emails have a much larger variety of TLDs. This is easier to discern when comparing the unique number of from TLDs seen, over twice that of the ignore emails. Also of interest is that .NET addresses have further prominence in the investigate population. On this visualization, the green represents when no attachment is sent. From this we can gather that investigate emails arrive with attachments more often. Though less distinguished but still interesting, looking at arrival day and times, we can see that ignore emails like to hit inboxes during the 8 a.m. hour, while investigate emails start strong at the beginning of the week and slowly tail off. Due to the large discrepancy in body length, it is not surprising to also find a big difference in vocabulary sizes between classes. Looking further into the top terms, we see that many of the investigate terms are aiming at stealing funds, while the ignore emails might be properly following the CAN Spam Act and allowing users to unsubscribe. A large issue I ran into during this project is that of data leakage. This was caused by emails that were part of the same campaign, with nearly exact copies of one another. These copies then had to be thrown out, as they would cause an unfair advantage if, for example, copies landed on opposing sides of the training and prediction sets. However, I also found emails that I could tell were part of the same campaign, but they had enough differences inside of them to still be usable. In this example, we can see the similar emails with nearly the same subject, but yet have different text bodies and from addresses. Because of these differences, emails like this could stay as part of the set, but time-consuming to find. The duplicate emails only added to the problem of not having a large quantity of investigate emails, though this is not an uncommon issue, as there are many other real-world problems where the minority group is the interesting or positive indicator. A perfect example of this is credit card fraud. I tried attacking this issue by using a combination of SMOTE, or synthetic minority oversampling technique, and undersampling the majority, but the best results I received was with just using undersampling of ignore emails. One benefit to the dataset being small, however, is that it enabled me to try multiple algorithms, because the time of execution is often short. Likewise, multiple feature sets were tried as well, consisting of non-text features, text features, and combinations of both of these. Based on these trials, I selected 2 feature sets and 3 algorithms to explore further due to their performance and stability against this dataset. The combination feature sets made the most sense to me, as this is what a SOC analyst would take into account, text and non-text, essentially anything they can. For combining features, I could not find a lot of information on this, but it would seem that either the sparse text features would need to be made dense, or the non-text features would need to be made sparse. This is so the features can be combined and one side does not dominate the other in the model. TF-IDF could be combined with binary on its own, or it could be made binary itself. I then used grid search to hypertune the parameters of the algorithms. Next, I used the tune models to build a voting classifier of both feature sets. I ran each set with several different seeded trials, as well as tenfold cross-validation. The 2 feature sets performed very similar to each other, seen here as the cross-validation results for each. But looking at the importances from the tree model for each set, the binary-binary features ended up with more terms in its important features than the sparse binary set. This enforces the earlier concept of truly taking into account both text and non-text features. After all, this is really what I'm after here, which is replacing and modeling a SOC analyst's mindset. Also, security is most often concerned with false negatives more so than false positives, as a false negative in this case would mean classifying an investigate email as an ignore email. False negative performance was another factor used in determining the best algorithms for the set. The final phase of this project was to see if the chosen model can be run on Splunk in order to take advantage of Splunk's data pipeline. Here I would be using custom apps like the one I built for Practicum 1 and the mail parsing app I built for this practicum, and then of course Splunk's machine learning toolkit, which allows Splunk to run sklearn models, pandas, and more. Of the algorithms chosen for my model, and as of MLTK version 3.4, I was missing some needed sklearn algorithms and a missing option on an existing one. Fortunately, Splunk makes this simple to add using their API. Since I had already previously added algorithms in the app created in Practicum 1, I added my new algorithms to that app as I consider it somewhat a continuation of that project. The algorithms I added were linear SVC, extra trees classifier, min-max scaler, and the current implementation of TF-IDF vectorizer in Splunk does not allow transformation to binary values. So I created a copy called TF-binary that allows and sets these options to produce a binary output. One algorithm I could not import into Splunk was voting classifier, due to how Splunk's API abstracts and cleans the options sent to the algorithm, but I was able to implement a hard voting rule using a Splunk eval statement. This is a simple majority vote wins rule. Looking at Python's workflow, we have a set order of operations to complete the prediction. While Splunk's order is a little different, the same basic building blocks apply. But in Splunk, this ends up being what is known as a search. One example of how the two systems are different is binning the continuous range values. In Python, both PandasCut and QCut were used to create appropriate spreads, while in Splunk, I simply use the range map command to implement the spread already determined in the Python version. The same tune parameters used in Python were applied to the corresponding models in Splunk, as well as an 80-20 split. As a conclusion, even with a small set, machine learning performed well at predicting the investigate emails with over 90% accuracy in Python and few false negatives. However, the Splunk model ended up with around 75% accuracy. Though Splunk and Python versions behaved very similar, there is clearly room for improvement. Possibly more settings in the mlspl.conf file, which sets limits to things like model size and memory usage, will need to be adjusted. One item I had not been able to figure out was that against the same 80-20 split, the Splunk model performed considerably lower than the Python version. One thought is that MLTK has a level of abstraction in which it is doing some things under the hood in Python that I cannot see or have control over, which will need to be looked further into. However, using this model created in Splunk and pitting it against 400 ignore emails that it had not seen since I had an overabundance of those, it then performed more in line with what I would expect. Since these are just ignore emails, the failed predictions here would be considered false positives. The final conclusion here is that combining text and non-text features creates a better model in this case, as together they make for an all-encompassing view of the data with which to model from. This model will be used in production, though I hope to continue to improve it. I wanted to append an update as I finally figured out what went wrong with my Splunk model. I was able to prove that it performed comparably. The problem was that I forgot to apply the pre-processing model's TF binary and min-max scalar to the prediction data. All icons in this presentation were made by FreePick from flaticon.com. Please see my GitHub repo for a list of references for this project and the associated blog. Thank you.